So anyway, welcome to this month's Journal Club, which is on kinetic mechanisms. It's a paper from the Journal of Biological Chemistry, quite an old paper, 1968 it was published. And the title of the paper is Kinetic Studies on the Mechanism of the Malate Dehydrogenase Reaction. And it's by Hayden Ainsworth. And I think it's interesting. It's from the Department of Biochemistry, the University, Sheffield, England. And I think it's funny that they call themselves the university. It sort of reminds me of football teams in this country, like the Ohio State, things like that. But in fact, actually, the department at Sheffield in the 60s was quite a spectacular department. Krebs, who was the chair at the University of Sheffield, had left and taken over the department at Oxford, where I was in 1967. But the people from Sheffield populated most of the major research universities in North America and became famous enzymologists, people like Gregorio Weber at University of Illinois Champaign, Vince Massey at Ann Arbor, Joe Shore in Detroit. Just a spectacular group of enzymologists were produced by the university in Sheffield, as they call themselves, including my mentor, Keith Diel. He moved with Krebs from Sheffield to Oxford. But so it's quite an austere group of people that Ainsworth and Haid came from. Anyway, I thought we'd start by talking a little bit about kinetic mechanisms and then go through the paper, because the paper is a typical enzyme kinetics paper in that it's very heavy reading because it's full of equations and things like that. So I thought to set up the discussion of what the results came out of the paper, I'd spend a little bit of time just talking about kinetic mechanisms. So I put together a few slides that talk about kinetic mechanisms. And so the first thing that I find students, and in fact colleagues, usually have a hard time with is understanding what is meant by the phrase kinetic mechanism. And the kinetic mechanism is simply a description of the order of addition of reactants, substrates or products, depending on which direction, to the enzyme. And it's a description of what types of enzyme reactant complexes are involved. It's a description of whether a steady state or a rapid equilibrium is involved with various steps in the reaction. And it's a description of the rate, or an assumption of the rate, usually, assumption of the rate determining steps in the reaction. And that sets up, understanding each of these things sets up understanding how you can derive information from initial rate kinetics of an enzyme catalyzed reaction. So, my next slide is, why is it useful to know the kinetic mechanism? Well, the first is that it's impossible to interpret in any rigorous sense values for Km and Vmax unless you know the kinetic mechanism of the enzyme. Km and Vmax are phenomenological parameters, but they have physical meaning depending upon the kinetic mechanism of the enzyme. And then if you know the kinetic mechanism, you have some understanding of where the rate limiting steps in the overall reaction are. And of course, both of those make a really good basis, not for just understanding the enzyme itself, but for understanding regulation. So it means you can then put physical interpretation on whether or not, or what regulators are doing, depending upon whether or not they affect Km or Vmax, etc., etc. And so before we delve into the paper, I thought it might be useful to give just a brief overview of how the kinetic mechanism of an enzyme is experimentally determined. And so it usually starts with doing detailed Michaelis-Menten kinetics in both directions of the reaction, the forward direction and the reverse direction. You need to do both if you really want to thoroughly understand the kinetic mechanism. So that's where it starts. And then various types of inhibition studies usually get involved in determining the kinetic mechanism. The main one of which is product inhibition studies, where you use a product of the reaction as an inhibitor versus the substrates in obviously the opposite direction. And that can be done in both directions, as in fact they do in the paper we're going to go into the details of. Another way of obtaining information is through using analogs of the reactants, and these are often referred to as analog inhibition studies. And then a final way that is often quite important is to use alternative substrates, not just the regular substrates, but many enzymes will use alternative substrates. And of course, malate dehydrogenase is a great example of that. It will use the pyruvate lactate couple. It will use the oxaloacetate malate couple. It will use the alpha ketoglutarate hydroxyglutarate couple with varying degrees of efficiency. And you can learn a lot about the overall kinetic mechanism by comparing alternative substrates. And then the final thing that is usually invoked in studying kinetic mechanism is to look at the consistency with independent estimates of dissociation constants and rate constants. And that comes from the fact that KMs and Vmaxes aren't always the things you think they are, but by knowing what they are from the kinetic mechanism and comparing them with independently determined rate constants or dissociation constants, you can get data consistent with a particular kinetic mechanism. So, moving on to the abstract, or the summary as they call it in this particular paper. Let's just sort of quickly go through the summary. So this work is a kinetic investigation of the reaction mechanism of malate dehydrogenase. And they go into a lot of detail about the preparation of the enzyme, because this is in the 60s, remember, this is before histag and easy purification. So the enzyme was prepared from washed mince of whole bovine heart, and they discuss in some detail the approaches and how it varies from other preparations at the time. Then they say the forward and reverse reactions catalyzed by this enzyme been studied at pH 8, which is pretty typical of what people do today. They use pH 8 as their main reference pH in the presence and absence of one product at a time. So they're getting into this product inhibition type approach to study the kinetic mechanism. And then as we go through the paper, you'll see there's a lot of detail about how they actually measured this. And this comes from the work of DL, who was at Sheffield when Hyde and Ainsworth were starting this work. DL had developed a fluorometer-based approach for measuring the concentration of NADH. And it actually brought back memories of my first days in DL's lab, reading the description of how they had to calibrate the fluorometer and use the fluorometer. The advantage of using fluorometer is that it's a much more sensitive method of detection. And whether you go from NADH to NAD or NAD to NADH, you can use much lower concentrations of enzyme, which means it's much easier to get true initial rates. And of course, all enzyme kinetics really depends upon getting true initial rates. And so using a fluorometer lets you more easily measure true initial rates. So they give a lot of description of how they did that in the paper. So they say they looked at product inhibition, initial velocity patterns in the absence of products. And I'll give you a simplified theory to think about that in a minute, and then the product inhibition patterns. And they say these are consistent with an ordered mechanism which has a kinetically significant ternary complex in which the coenzyme substrate combines with free enzyme, and we'll talk the significance of that. And then they determined all their Michaelis-Menten Km values, and you can get inhibition constants and dissociation constants. And they bring up an important point then in the abstract, in the summary. The dissociation constants determined for coenzymes acting as substrate differ from estimates of the same constants obtained by studying the coenzymes as product inhibitors. And then they bring up the point that these effects may be related to substrate inhibition by oxaloacetate and substrate activation by malate, which have been observed previously. And so in the paper, they're going to discuss stuff about the substrate inhibition, substrate activation as well. Okay, the rate constants calculated for the separate reaction steps reveal that the simplest ordered bye-bye mechanism, that's using Cleland's terminology, does not apply, but they are consistent with an ordered bye-bye mechanism in which there's conformational changes, or as they call it, in which enzyme oxidized coenzyme complexes isomerize, euphemism for conformational changes. And then, as with other dehydrogenases for which this condition applies, the possibility cannot be excluded that the enzyme-reduced coenzyme complex may also isomerize. And we'll talk a little bit about that as well. So this is the scheme, that they're ordered bye-bye type scheme. If you're not familiar with Cleland nomenclature, he has ordered, he has bye-bye, and bye-bye simply just means there are two substrates binding to give a ternary complex, and then two products leaving to regenerate the free enzyme, and then they define these. And Cleland, of course, is the person that's invented the phrase ping-pong mechanism, where you get one substrate binding one product being released, a second substrate binding another product. So you get this sort of, so-called ping-pong type mechanism. Now, I don't know, Evie, whether or not you've spent much time looking at the actual paper ahead of the session, but it is full of amazingly complicated equations. And I find those equations drive students absolutely mashugana. They're equationophobes at the best of times, but describing in detail all of the equations and they're perfectly good equations, and but DL, who was the sort of godfather of enzyme kinetics in the 50s and 60s, developed a much simpler way of representing rate equations. and it's called the generalized rate equation. And it represents, the enzyme concentration over velocity. So it's a Lineweaver-Burke plot type equation, because that's an E over V or 1 over V type start, is equal to, and he called these things initial rate parameters, or sometimes they just get called phi parameters. But for a 2-substrate enzyme, whatever its mechanism, there are 4 initial rate parameters. And the generalized equation is phi0 plus phi1 over S1 plus phi2 over S2 plus phi12 over S1 times S2, that should say. Sorry, my bad typing. I'll change it when I put the PowerPoint up on the web later. But that should say S2, S1 times S2. And of course, this describes a series of Lineweaver-Burke plots where you plot 1 over V against either 1 over S1 or 1 over V against either 1 over S2. And you can rearrange this equation very simply and get and experimentally determine values for each of the initial rate parameters. And to me, and obviously to DL, who developed this approach, and it's been used by many, many people. I think far more people use this approach that do full kinetic studies than use the Cleland equations and the more detailed equations, because this is much easier and it gives you parameters that are dependent upon data, not upon the assumption of a mechanism. Whereas the Cleland approach or the other approaches, you have to assume a mechanism before you can get the equation. And we'll talk a little bit about that, because it gives rise to some funny looking plots occasionally. So
Alice, do you spend time deriving these equations for students, or do you
the generalized equation can be derived, and I usually, for students that want to get into it, and it's in one of the papers that I'm going to refer to in a moment, shows the derivation of the generalized rate equation, shows the relationship of these to all the constants and things. And I'll put that up on the web as well. But I do show them how to rearrange this equation so that it fits the Lineweaver-Burke format, because the experiment I want them to do is to determine the initial rate parameters, because that's where they're going to calculate their true Vmax and their true Kms, rather than their apparent Kms and apparent Vmaxes. And I've never yet found much use in apparent Kms and apparent Vmaxes because they have no physical significance. You need the true, and these are related to the true Kms, as I'll show you in a minute. So anyway, the basic types of 2-substrate reactions that fit this equation, the compulsory ordered steady state, and now we're introducing not just compulsory order, where you have a required addition of substrates, but you're introducing the term steady state. And so we usually talk about what the steady state assumption is at this point. And it's really important to understand enzyme kinetics to appreciate that you can be either steady state, or you can still be compulsory order, but be in rapid equilibrium, because those two terms have inferences for where the rate limiting steps in the reaction are. And that impacts the physical meaning of the Kms and Vmaxes. So, if you just say it's compulsory order, but you don't say whether it's steady state or rapid equilibrium, you're really not talking about a kinetic mechanism. You're talking about the order addition of substrates, which isn't the kinetic mechanism. It's part of. So we talk a little bit about steady state and rapid equilibrium assumptions usually at this point. And then you can have random order where either S1 or S2 binds. And again, it can be random order in a rapid equilibrium between complexes, or it can be in, sorry, this is the rapid equilibrium. This is the steady state version where you've got individual rate constants. Whereas in the rapid equilibrium, you put equilibrium constants. And then it could conceivably be an enzyme substituted mechanism or a Cleland nomenclature ping pong mechanism where substrate binds, product release, substrate binds, product release. But to really understand the kinetic mechanism and kinetic data, you need to understand, as I said, steady state versus equilibrium and ordered random order versus compulsory order. And then this table, and again, it's from one of the papers that I'm going to share on the website, shows you the relationship of the initial rate parameters to the various constants that are in the schemes. And you'll see in many of these initial rate parameters are whole bunches of different rate constants from the mechanism. And because these are related to the slopes and intercepts, they're obviously related to the Vmax and Km. So Vmax, the true Vmax is simply 1 over phi 0. And you can see, depending upon the kinetic mechanism, it's either a complex set of rate constants or it's a simple single rate constant. And you'll notice these are the rapid equilibrium mechanisms where the Vmax is a single rate constant. But in the steady state mechanism, it's a very complicated set of rate constants. And that's why I say you have to understand what the overall mechanism is so you can interpret, where possible, what Km and Vmax actually mean. Because these relationships, some of them are simple dissociation constants or rate constants, but they're not always the dissociation constant that you think. So for instance, for Km for the first substrate in a random order rapid equilibrium mechanism, it's the dissociation constant, not from the free enzyme, but from the ternary complex. And likewise, the other dissociation constant that you can get is not from the free enzyme, it's from the ternary complex. It's only in a compulsory order rapid equilibrium mechanism that you actually get Km for the second substrate is in fact the dissociation constant from the free enzyme. So again, understanding the kinetic mechanism lets you interpret Kms and Vmaxes appropriately. Without that, it's really difficult to put any significant meaning to Km values. Okay, so all of what I've just is in this article, and it actually goes through and derives the phi parameter equation for one of the mechanisms, just as an example. But I'll put this up on the website. So let's go to the data in the paper. And this is a major difference in approach. So this is their figure 1, which is simply the effects of NADH on the initial velocity of the forward reaction with oxaloacetate as the varied substrate. Okay, and so they get all of these different lines, different data points at different fixed concentrations of NADH. So this is the highest concentration of NADH. This is the lowest concentration of NADH that they used. And they get, now, if you look at that and look at the lines, you go, oh my God, this line doesn't go through any of the data points. Or this line, this doesn't even, and what they do, and they describe how they've done this, what they've done is a global fitting of the whole graph against an assumed mechanism. So they've assumed that ordered bye-bye mechanism and fit the whole graph against the assumed mechanism. So none of these lines are fitting to an actual Lineweaver-Burke data set. They're fitting globally to the whole experiment. And that can lead, at least in my mind, and DL's mind, which is why he invented the approach he used, and many of us do, is we like to fit the data to get the parameters rather than fit the whole data set assuming a mechanism. Now, they point out in the paper that the lines were linear. Well, some of these don't look terribly linear to me. This one, I could easily see a line through that part and another line through that part. So, you can make the argument looking at some of the data sets in here that they're not actually linear Lineweaver-Burke plots. Now you go, okay, this is OAA, maybe I'm seeing substrate inhibition. What does a Lineweaver-Burke plot look like when you have substrate inhibition with the varied substrate? Well, if you start at the lowest, it gets faster and faster and faster, but then it gets proportionally slower, and eventually it would curve up, and you'd get a line like that then curves up. So it may be that they're seeing some bias to the data by seeing some starting of substrate inhibition. And you can see that trend actually in almost all of these lines, where maybe the slopes aren't quite what they think they are from this global fit because of substrate inhibition. So you have to be very careful when you do this sort of experiment. And again, this is now the other direction experiment. And again, they've done the same thing. They've globally fit the data. And again, I'll take this lowest data set. To me, there's some nonlinearity to that. Now, I bring that up because that's very significant, because a number of dehydrogenases have been shown to have cooperativity in cofactor binding. And in a Lineweaver-Burke plot, negative homotropic interactions would show themselves by exactly the sort of data they see here. So, and again, several of these plots seem to sort of be biphasic. And so this global fitting is not necessarily the best way to do enzyme kinetics. And it probably gives rise to the fact, so now they put the table of their Michaelis constants and dissociation constants, and you'll see that they've got plus or minus, 20 or 30% errors in these constants. And, one of the nice things about enzyme kinetics is you can get really good data if you do it reproducibly enough, and getting plus or minus 30% errors or more in some of these cases just seems that maybe this is because that wasn't the best way to fit the data. And then they get all their kinetic constants. They do the product inhibition studies. And I'm skipping over a lot of the graphs because they all look like the ones we've seen in Figs 1 and 2. But they do this global fitting and get all their slopes and intercepts. That lets them calculate apparent KIs from slopes and intercepts, etc. And they get all of their data. And again, the errors sometimes are very good, but sometimes are not so good. So, the consistency of the data makes it hard to judge the real values. Though having said that, I should go back to this, because these are the KMs and values that pretty much are throughout the literature for malate dehydrogenases. Some people have them with much smaller errors, but they're all in this range. So it's not that they're way out of range. It's just, they may be missing something in the data. And so with that, the paper ends up concluding that, as we talked about in the summary, that this is an ordered bye-bye mechanism. And I want to just quickly talk about a couple of the other papers that were on the list. This is a paper from Ann Arbor, Dan Beard, and they do essentially similar sorts of experiments. Okay, they do progress curves and the forwards are reverse. One of the nice things about this is that they use varying pHs. They made sure that their physiological ionic strength was constant. They did different pHs. So pretty much the same set of conditions. And they come up with a very similar mechanism, but they acknowledge the fact that there's a pH dependency of the kinetic behavior. And of course, there's a proton in the reaction. So of course, there's going to be a pH dependence. But they have additional states to explain the pH dependency. And they end up concluding, we believe this to be the first kinetic model obtaining both substrate and pH dependency. And they're correct. They did a nice job in this paper. But, basically the same kinetic mechanism. This paper, however, is an interesting paper because it really delves into the whole idea of the substrate inhibition and what I'm going to call abortive complexes. And this is a technique that very few people do anymore. There are a few practitioners of this, and it's isotope exchange kinetics at equilibrium. So this isn't an initial rate dependence. They measure isotope exchange. So for instance, they put an isotope in oxaloacetate that's going to show up in malate, or NAD that's going to show up in NADH, etc. And then they look at the rate of exchange at equilibrium, and it lets them change concentration, pairs of concentrations of substrates at the same time. And it's probably the best experimental technique out there for determining whether or not you get these non-productive, or as I usually call them, abortive complexes. Because in essence, if you vary the concentration of a pair that forms an abortive complex, it will slow down all of the exchanges. So it's a cool way to look at whether or not you're forming abortive complexes. But again, the key is that it's the same basic kinetic mechanism they come up with. So this result supports a compulsory binding order in which oxaloacetate and malate will bind to enzyme-reduced nucleotide or enzyme-oxidized nucleotide complex, but don't bind to enzyme devoid of bound coenzyme. So, you know, it's, again, all of the studies are consistent with the basic kinetic mechanism, but not all of the studies give information about abortive complexes or give us accurate information. So, you know, it's pretty consistent what the kinetic mechanism is. It's an ordered ternary complex mechanism where cofactor, whichever direction, has to bind prior to the keto acid or hydroxy acid substrate. So what I want to end with is a couple of papers that aren't about malate dehydrogenase, but they illustrate some of the things that can be done to get around some of the issues that are raised in all three of the papers, which is about rate limiting steps and things like that. So Sarah Wacker, who was actually a high school student in Joe Provost's lab before she came and joined my lab at the University of Richmond, did a wonderful job using isotope effect studies to look at rate limiting steps. Because of course, if you've got a rate limiting step and you put an isotope, then it can reveal that that step was in fact rate limiting. Whereas if a conformational change, which is one of the possibilities that's brought up in all three of the kinetic mechanism papers on malate dehydrogenase, suggests is rate limiting, an isotope effect will not change a conformational change rate limiting step. And so, you know, I think it'd be really cool for somebody sometime to actually do basically a parallel study to this study with malate dehydrogenase and look at, you know, what truly is rate limiting, whether it's conformational change or whether or not it's one of the rate constants for substrate binding or chemical conversion, etc., etc. And then another thing that's brought up, and I thought I'd share this paper, that they bring up in the discussion of the various papers we sort of talked about the initial rate kinetics data, is whether or not there are multiple sites for cofactor, because that could be used to explain cofactor activation in malate dehydrogenase, or multiple sites for the substrate, which could be used to explain the substrate inhibition or the substrate activation phenomena that's seen. But enzyme kinetics is not possible to reveal whether or not you've got multiple sites for a given substrate. You can infer them, but you can't prove them by enzyme kinetics, because every single kinetic plot that you can get can come from some combination of steady state or equilibrium effects. And, you know, so non-linear Lineweaver-Burke plots or non-canonical Michaelis-Menten plots are never or should never be used to suggest that there are multiple sites for the ligand, because there are so many other explanations. So with glutamate dehydrogenase, where a lot of these conversations started and paralleled the conversations that are going on nowadays with malate dehydrogenase, a group of us developed a method using NMR that used transfer nuclear overhauser effects to look at whether or not there were multiple cofactor binding sites in distinct binary or ternary complexes in glutamate dehydrogenase. And so again, this is the sort of thing that somebody needs to do sometime with malate dehydrogenase to show whether or not the non-linearity that's observed in some of the initial rate kinetic plots is in fact due to multiple cofactor sites, for example. And so with that, I'm going to stop sharing. And Evie, if you've got any questions, now's a good time to ask them.
Yes. So, what exactly are abortive complexes? Is that like a
right,
non-productive pathway in the mechanism?
Basically, what happens? So in an abortive complex, a product dissociates, but the equivalent substrate can now bind, because the binding site for alpha ketoglutarate is this, or oxaloacetate is the same binding site for malate. If the oxaloacetate leaves, malate could bind in it. But if malate binds before the cofactor is dissociated, it's what's called an abortive complex.
Oh, okay. Okay.
And so that's the power of the isotope exchange at equilibrium, because you can vary things that you think might form abortive complexes. And if they slow all the exchange rates, you've got evidence that, yes, they were abortive complexes. If they don't slow the exchange rates, then you know they didn't form an abortive complex. And abortive complexes are the usual explanation for this substrate inhibition that you see at high concentration of substrates in lots of enzymes. It's not just malate dehydrogenase. But nobody's ever demonstrated conclusively that it's due to abortive complex formation. There's an assumption that it is, just because that's been shown in other dehydrogenases. But nobody's ever demonstrated it experimentally.
Okay. Okay. And this is seen at the higher concentrations, or
at higher concentrations of oxaloacetate.
Okay.
When you go from oxaloacetate and NADH to malate, but it's also seen at higher concentrations of malate when you go in the opposite direction.
Okay.
And as I say, it shows up in a Lineweaver-Burke plot as an upward tick towards the y-axis, and it shows up in a Michaelis-Menten plot as a downward curvature from the Vmax. And those are often reported in the literature for malate dehydrogenases.
Okay.
But as I said, nobody's ever shown
that it's exactly
what the physical interpretation is. And it's important to know that, because when you think about regulation, you might regulate by modulating the abortive complexes.
Exactly. Yes.
And knowing how they're formed and what the mechanism is really important if you want to understand how the regulation works.
Now, in the mitochondria, when we're thinking about the TCA cycle, let's see, NADH binds tighter than NAD.
Yes. And that's actually a ubiquitous phenomenon for dehydrogenases. It doesn't matter which dehydrogenase you look at, they almost always bind the NADH more tightly than they bind the oxidized cofactor.
Are there any conditions in which the oxaloacetate, when you're thinking about the TCA cycle, the oxaloacetate gets high enough that it may do an abortive complex? Because typically we talk about, like it's a non-spontaneous, but it's a circular thermodynamic pathway.
Yes.
And so the assumption is that there's never a backup. It just goes, it keeps on going.
Yeah.
But are there any conditions that that is not the case? That
Well,
there is a little
I
bit of a
right.
accumulation and you start seeing the product inhibition,
Well,
possibly?
so looking at the physiological concentrations of the Krebs cycle intermediates has become an interesting thing to do. And there's a bunch of data out there. Interestingly enough, a lot of it derived from Krebs' original group by a guy called Richard Veitch, who worked at NIH for a long time, studying intracellular concentrations of metabolites. Um, so there's a fair amount known, and it's becoming apparent that various physiological conditions can alter those concentrations and maybe build them up to levels at which they would become substrate inhibiting. Um, so there's quite a bit of interest in that. Um, you know, so, and of course, what applies to the mitochondrial enzyme and what applies to the cytosolic enzyme, you may have different effects, even though they both show the same basic kinetic mechanism. And I'm pretty sure that both cytosolic and mitochondrial show the same substrate inhibition type effects. But the conditions in cytosol mitochondria
It's different, yeah.
may be
There's,
different, and you may be seeing differential effects.
mhm.
So
And
lots
so
of cool things to do.
in the so when we cover bimolecular kinetics, right? So the whole like random disorder, random
Right.
ordered ping pong. Um, the way that textbooks cover it is like it is what you mentioned originally with the apparent KMs and then
Right.
um
And the trouble with the textbooks is they rarely go into this thing that I emphasize about steady state versus rapid
yeah,
equilibrium.
yeah,
And it's only, basically people that have followed DL's work and, understand the differences between steady state and rapid equilibrium. It's important for students, I think, to understand that those impact the interpretation of the
okay,
KMs. And actually, the paper that I showed you is the core of something that's going to course source soon. So
okay,
hopefully it'll be in course source in the not too
okay.
distant future.
Yeah, I look forward to seeing that because they have a lot of they it's challenging for them to think because the way the textbook has it,
Yeah.
um, they don't go into the explanation too much.
And
And
then
so
they go
they
into a paper like the one we were looking at, and they see all
yeah, and
these
then they
humongous
grapple with what's
equations,
yeah, what
and
are
they
they
go,
looking
no,
at?
this isn't for me. But in fact, enzyme kinetics can be made, as DL
Yeah,
does,
okay,
much more intuitive and phenomenological without getting rid of any of the rigor,
okay,
but making things that let you measure things that are physically interpretable.
okay. And they have a better time with DLs
Oh,
than
yes. Oh,
okay.
much. And it's funny because I've had students go to national meetings and present kinetic data and show the DL equation. And, somebody famous will come up to them and say, wow, you use the DL? Yeah, I learned how to do that when I was at Duke, because I taught it at Duke when I was
Uh-huh.
at Duke. So they keep running into people that understand this and understand the power of it, which is
Okay,
sort of
good.
fun.
Good. And that paper is going to be linked in the
Yes, yes,
okay,
yes.
good, good, good. Yeah, because I haven't seen it in that format, I have to say. But yeah. Yeah, we used global fitting and
Right, right.
the full Michaelis-Menten equation
Yeah.
and um yeah, yeah, and depending on what enzyme we were looking at, we did get deviations in the
Yeah,
fit. So
yeah.
this is interesting.
And
Yeah.
that global fitting, to my mind, tends to hide some of those deviations that may be telling you important things.
Yeah. Yeah. Exactly.
Yeah.
Thank
Well,
you.
anyway, Evie, I hope this
Yep.
was useful. I'm glad you had the time to join. And
Yes. Yes. Thank you. This was very useful.
good. Well, I'm going to stop recording.
Mhm.